Hi, I'm going to review the Chapter 12 material with you. So we're going to cover increase, decrease, minimum, maximum. We'll cover vertex form, standard form, and factored form. So I'll dive right into this first problem where we're going to identify all the characteristics that are on the left-hand side here. So it's a lot of information, but let's take it one at a time. So first of all, the quadratic itself, the y equals negative 1/2 x plus 2 x minus 4, that function is in factored form. I'm sorry, yeah, it is in factored form. So that's the one that tells us our zeros right away. So I know that if I take x plus 2 and I were to set it equal to 0, that would tell me that I have a 0 at negative 2, 0. And then I can do the same thing with the other one. And like I taught you in class, it's opposite on the inside for a reason. And that reason is if you set each one of these equal to 0 and solve, it turns into the opposite. So your other 0 is at 4, 0. So right away, I have 2 points on my graph. Now what I'm going to do to figure out the rest of this stuff is throw it in my calculator, which I'll pull up on the screen so that you guys can see exactly what buttons to hit. So what we're going to do is go to y equals on the top, and I'll put in negative 1/2, or you could even put in negative 0.5, and then just throw it in parentheses right as you see it. So I have x plus 2 and x minus 4, and then I also give you the window. And if we want to make the most accurate sketch, we're just going to follow the window, which is from the x values going from negative 5 to 5, counting by 1, and then the y values also from negative 5 to 5, counting by 1. Now I just hit graph, and notice it crosses at negative 2 and positive 4. So that's why it was that whole opposite on the inside of those parenthesis things, that I had x plus 2, and notice my 0 is actually at negative 2. But now that I have my sketch, what I want to do is calculate the vertex. So I'm going to hit second and trace. And since this parabola has a negative a value and it opens upside down, that's an indicator that we have a maximum. So that's what we're going to find. So once left bound, so notice my cursor is flashing to the left of my 0, and now I'm going to move, to the left of my maximum, and now I'm going to move it to the right of the maximum, and then I'm just going to move it right between those two, somewhere towards the top. And I have a maximum 0.9999, that's basically 1. So my maximum x coordinate is 1 and the y coordinate is 4.5. So I have a vertex at 1, 4.5. So I'm going to go ahead and plot that point. And then I'm going to draw on my parabola. And this might be ugly. That was ugly. That was not as bad, but it's still kind of ugly. Okay, so now we go on to these domain range intervals. Actually, before we do that, let's just circle here. I have a maximum. If I ask you for your maximum value, I'm referring to the y coordinate. Your maximum value itself is 4.5 because you think of that highest or lowest point. And when you think of highest or lowest, you should be associating that with going up or down like the y-axis does. So that's why it's the y coordinate of the vertex. That is the highest, most possible point you could get to. And now we start talking about interval. So the domain is basically all of these x values starting from all the way on the left, and look at, again, for every x value you're going to have a y value, so that's why it's from negative infinity to positive infinity. Now as far as range goes, all of these values are in your range, but notice once you hit this point, everything above that is not in your range. So that one is going from negative infinity, but then it hits this point right here, and that point is part of your range, and that point is the 4.5. And since 4.5 is part of your range, we are going to put a bracket on there so it's closed. And again, that indicates that this point does exist. That point is at 1, 4.5. So that's why it's a closed bracket, is if it is included. As far as interval goes, now we're looking at x values. I'm looking at basically where is my function increasing, and it looks like that is from negative infinity. And again, we're focused on the x-axis. So look where my cursor is. The function is increasing, 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 increasing. Then it just stops. Because I'm at this point right here, it is not increasing. It is not decreasing. It just stops increasing, basically. And we look at the x value, and that is the x value of 1. So this is from negative infinity to 1. and then it would be decreasing from 1 to positive infinity. Again, we're looking at the x values, which is a little bit confusing here, because you would think that it'd be like a negative infinity because it looks like the graph is going down, but we're not talking about if it's going up or down. We're just reading the x-axis going left and right here. So once you are at an x value of 1, every x value past 1 all the way to infinity is going to have a decreasing value on the parabola. Next one. Now I've got, wait, was that really from, oh, here's 2. Okay. Graph the following function using the graphing calculator, and then we're going to identify the transformation from the graph, and I'll explain that in words. So first thing I'm going to do is put this in my calculator. This is in vertex form because it is in the form of f of x equals a x minus h squared plus k. And that was the vertex form where hk itself was your vertex. So I'm going to go ahead and put this in my calculator. I'm just going to use 0.25 instead of 1/4. You can use either. I'm using my actual calculator and not the crappy computer one. And it looks like mine's just as crappy. Scary. Okay. +1. This graph better work. It's being a poop. Bam. Okay, and then let's keep the same window from -5 to 5, counting by ones. Sweet. Okay, so right away from this information, again, it's opposite on the inside. So your x-coordinate of your vertex is not -3. The x-coordinate is +3, and your y-coordinate is up 1. So this vertex point is going to be over 3 and up 1. If I asked you right now if the graph was opening up or down, you should be able to answer, and hopefully you're saying up because this a value is 1/4, which means it's positive. So if I make a little sketch of this thing based off of what my graph looks like on my calculator, it's going to look something like this. Looks like your y-intercept is actually 3. Either way, as far as the transformation goes, from f of x is x squared to from what I have in green to what this function is. The transformation. Here's what I would love you guys to say as far as justification goes. The vertex translated 3 units, that's a really ugly 3. 3 units to the right, blah, 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 and 1 unit up. So again, imagine that f of x equals x squared looks something like this. And then our graph itself, look at the vertex point. It's shifting to the right 3 and then up 1 because of the x minus 3 and the x plus 1 here. So that's the translation. If you were to, in your calculator, put this green function in here, f of x equals x squared, and you put that under y2 when you do your graphing, if you graph both of these functions, you would see that the one in the red is going to be wider. And the reason is this 1/4 value, so I'm going to say this right here, since a, because this is my a value, is greater than 0, but less than 1, the graph widens. So you could also say that the 1/4 value, the a value, dilates your graph. We use the word dilate instead of translate. A translation is a shift left, right, up, or down. Dilate means to stretch it or shrink it. So in this case, the 1/4 is going to stretch our graph out. If we had a value that was greater than 1, if we had like a value of 3, it would make the graph really, like the parabola, really skinny. And another thing to note is if a is less than 0, that would flip the graph downwards, so then it would be like a reflection over whatever axis, like the x-axis in this case. And that would be if the a value were negative. Next one, so now we have the vertical motion model. So an object is launched directly upward at 64 feet per second, so that's going to be the starting velocity, which we're going to call v0, and it's from a platform that is 80 feet high. So this rocket is, or this object is already 80 feet off the ground. and we want to know what the maximum height will be and when it'll attain the height. Notice my a value is negative in this formula, which means my function is going to look something like this, and that's why we say find the maximum height, is because it is a maximum value. If this a value were positive for whatever reason, it means that your parabola would open upwards and that you would have a negative instead. So throw this in the graphing calculator and then change the window to match exactly what I have up there. I'm going to do the same thing. So negative 16x squared plus, I'll write this down as I'm doing it. So f of t, if I substitute the values incorrectly, will be negative 16t squared plus your initial velocity, which is 64t, and then you would say plus your initial height, which is 80 feet. So I'm going to put that in there just as I see it. And then I'm going to adjust my window. So we're going to go our x values from negative 2 to 6, which really means before the rocket was launched, the negative 2 is negative 2 seconds. And we're going all the way to 6 seconds. And as far as the window goes, we're going to go from negative 50, which I know we can't have a negative height, but just to make my window kind of big enough, and we're going to go all the way to 250, which is hopefully above our maximum a little bit. And on my graph, which I'll make a little tiny sketch of, on my graph it looks like this on the picture. So as far as this maximum point, that's what we want to calculate. So I'm going to write this down. We want to calculate the max because we want to know what the maximum height is, and we want to know what the time is when we get there. So if you think about the graph, your height is modeled on the y-axis and the x-axis is time. So if we think about this coordinate right here, your x value of this coordinate will be the time that it takes to get to your y coordinate, which is the height. So that's what it wants in both of these questions. Both of these questions says, what will the maximum height be, and then when will it attain it? So basically, if we just solve for this maximum, that's going to answer both of our questions. So I'm going to hit second trace. I'm going to go to max, and I'm going to calculate the max just like I did before. And I get a maximum of 2 and 144. So as far as the problem solving standard, I would love it if you guys could answer this in a complete sentence. So what you would say is after 2 seconds, or at 2 seconds we could say, the object reaches a maximum height of 144 feet. Okay, now if I go a step further, which I'm not asking you to do this in this problem, but if I were to go a step further, I could ask you how long it would be before the rocket hits the ground. So think about that. Think real quick according to the model. The rocket gets launched up, blah, 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 hits the ground right here. This is what you would be solving for. If I were to ask how long would it take for the rocket to hit the ground, you would have some kind of x coordinate and your y coordinate would be 0. 0 because when it hits the ground, your height is 0. So if I were to ask you how long it takes for it to hit the ground, you would do second. Let's write this down for you. You would do second, you would go to trace, and you would calculate the 0 that is over here. And you would get exactly how many seconds that is before the rocket hits the ground. And I can even go a step further, and I could also ask you for y-intercept, which is where the function actually starts from. And hopefully, without even looking at the graph, you guys will be able to tell me 80 feet, because that was our starting height. So that is your y-intercept. At 0 time, the height is 80 feet. 2 more. Matt is building another room off his house, and he wants the perimeter to be 75 feet. And I want to know what are the dimensions of the room that would maximize this area. So he is building this off of his house. So I have a width here, I have a width here, and I have a length here. I'm assuming that this side of his house he's not going to add more material on. So we're talking about 3 sides here. And I'm hoping that this thing works out. So let's make our formula first for the perimeter of this. And I know that the perimeter of this would be basically taking width plus your other width plus your length. So 2w plus L. And we know that that perimeter is 75. He wants to use 75 feet of material. So what we're going to do in the problems that you'll see on a test or a quiz, the first step that you would do is really get this length by itself. If it wants your area in terms of width, you want W to be the variable, which means I'm going to have to bring this whole 2W to the other side and get that my length equals negative 2W plus 75. So that's part of it. To do the other part, we need to figure out the area calculation. So I'm going to use the area formula, which you guys know is area equals length times width. And now what I'm going to do is just substitute this value, or this quantity of negative 2W plus 75. I'm going to substitute that for L. So I have negative 2W plus 75, and I'm going to multiply that by W. So we're going to use that little distributive property here. And what that'll do is give me my area in standard form. So negative 2W times W is negative 2W squared, plus 75 times W is just 75W. If I said to write this in standard form, this is standard form because your W's are going from highest power to lowest power. You want your squared term to be before the one that just has just the W, or just before the constant. Now that I have this, I want you to throw this formula into your calculator. And I even put the window up there again. You guys will be provided these windows on an assessment. So I have negative 2x squared plus 75x. Adjust the window. So my window is going from 0 to 50, meaning your x value, which for us is our width. So our width we're saying is going from 0 to 50 feet, and then the y values on your calculator actually represent area. So I'm going to have those from negative 50 to 1,000. And then I'm going to hit graph, and I'll draw you the little pretty picture that mine gives me. It's glorious. Okay, so it looks something like this. And we want to know basically what width, so what x value would maximize the area. So basically, again, we want to find the maximum, which W is our x coordinate, area is the y coordinate, we are solving for the x coordinate. So I'm going to do the same thing from before and hit second trace, and I'm going to trace a maximum value. Left bound, I'm going to right bound, and I would suggest you guys try this yourselves, and it looks like I am getting a width of 18.75, and that would be feet. And that width of 18.75 feet gives us a y coordinate, or an area of 703.125 square feet. So if I want to figure out my length of this, all I'm going to do is take this 18.75 and substitute it in for W. So my length is negative 2 times 18.75 plus 75. Break this apart, do the order of operations. I'm going to take negative 2 times 18.75, which gives me negative 37.5, and then I'm going to add 75 onto that, and I get a length here then of 37.5 feet. Okay, so the length again was twice the width in this case, and that's where again these numbers are coming out to, is because I just substituted this into there. Alright, what is next? Okay, last problem. So this one is just going to talk about second differences and first difference. So it says list 4 numbers that have a constant first difference, and I want 4 numbers that have a constant second difference. List what types of functions have a constant first difference and which ones have a constant second difference. So if I'm talking about 4 numbers that have a constant first difference, I'm talking about like skip counting. So let's say I start with the number 2 and I add 3 to that. Gives me 5. If I add 3 to that, I get 8. And if I add 3 to that, I get 11. What I mean by taking a first difference is if I work backwards and take 11 minus 8, I get 3. 8 minus 5 is 3, and then 5 minus 2 is 3. So this is my first difference, and it is constant, meaning this 3 is the same number, which means that for us, knowing what type of function this is a linear function. Linear functions have a constant first difference, and they have 0 for a second difference. So if you go one step further, 3 minus 3 is 0, and then this 3 minus this 3 is also 0. So Again, just to recap that though, linear functions have a constant first, and they have 0 for a second difference. Quadratic functions, on the other hand, are going to have a constant second difference, which means the first difference is not going to be constant. So if I want to create 4 numbers, then I'm going to have to increase them all by the same amount every time. So what I mean by that, let's start off like what I had before. From 2 to 5, I'm increasing by 3. Now what I could do is maybe increase by 4. So if you increase this by 4, I'm going to get to 9. If I increase from 2 to 5, I jumped 3. From 5 to 9, I jumped 4. Now from 9 to the next term, I'm going to jump 5. So 9 plus 5 is 14. Now watch what happens when I take these differences. 14 minus 9 was 5. 9 minus 5 was 4. And 5 minus 2 was 3. So when I took my first difference, these are not constant, which tells me that it's not linear. If I go ahead and take a second difference now, 5 minus 4 is 1, and 4 minus 3 is 1. Now that I have a constant second difference, that tells me that this function is quadratic. Okay, so I'm not going to ask you on a test or a quiz to come up with the 4 numbers, but I would expect you to know that linear functions have a constant first difference, and quadratic functions have a constant second difference.